First, we're going to review some preliminaries, which is basic fundamentals of algebra that you should be aware of before we get into actually working with algebraic expressions. So we're going to talk about properties of exponents and radicals first. These two things can be found on page 12 and 16 of your textbook, but we're going to go over them now just so that you're familiar with them. But the complete list is found on those two pages. Before we start looking at properties of exponents, we should talk about what an exponent actually is, its definition, and it basically represents the number of factors present for a given base. So, for example, if my base is 2 and my exponent is 3, it just says that I have 3 factors of 2, or 2 times 2 times 2, which is 8. There are 3 factors of 2 present in the number 8. If I had another number like 2 squared times 3 cubed, means that would be a number with 2 factors of 2 and 3 factors of 3. So it represents the number of factors that are present for a given exponent. Now with that definition, we can kind of derive several properties. So the properties we're going to go over right now can be found in that review page of your review packet. So if you open that review packet to this page, the formulas, these ones are the ones that you should have already been familiar with from Algebra 1. The product of the same base raised to given exponents, you would add those exponents. Division would be subtraction. Anything to the 0 power is 1. It's the identity property. Exponents raised to exponents, you would multiply them or you get a product. And exponents distribute across multiplication. So if I have ab to the m, it's a to the m times b to the m. Now the two new ones that we did this year were negative exponents, which we found out actually just represented fractions. So this would be 1 over, or 1 divided by, a raised to that m power. The other property we noticed is that exponents can also be expressed as radicals, and radicals as exponents. That's with the rational exponent property. A to a fractional exponent turns out to be actually represent as a combination of exponent and radical. So here are a couple of examples of that. If I had 2 to the 3 halves, I could rewrite that as the square root of 2 cubed, or as the square root of 2 to the 3rd power. So that's using this rational exponent property. For that reason, all of these properties of exponents have corresponding properties of radicals, where you can convert any radical into an exponent and use those properties. So here's a couple of examples of applying these properties. Let's go through these. First off, it's simplifying. For my first question, I'm going to distribute this cube to these 2 powers. So this will be negative 2 to the 3rd power, which is negative 8. Then I have x squared to the 3rd. And when I have exponents raised to exponents, that will be multiplication. So x to the 6th times, this negative 1 distributed would be 4 to the negative 1 power. X to the 3rd raised to the negative 1st, product again, negative 3, all divided by 2x squared. Now notice that since there are parentheses around these, this as exponent applies to everything within those parentheses, whereas there's no parentheses here, so the exponent is only applying to the x. To continue simplifying, I'm going to combine my like terms. The first thing I'll do is get rid of these negative exponents so I don't have to deal with them. So I'll have negative 8x to the 6th divided by this 4 to the negative 1 becomes 1 over 4 to the 1st, or just 1/4. And when I have 1/4 times the 2, it'll give me an 8 in my denominator. I have x to the negative 3. X to the negative 3 will be 1 over x cubed. So I'll have an x cubed in my denominator. And when I combine that with the x squared, that gives me x to the 5th. Now it's pretty easy to see how this simplifies. Common factors of 8. They'll cancel out. And I have x to the 6th over x to the 5th. That will result in x to the 6th minus 5 or x to the 1st. This whole thing is just negative x. Next example. I have to be negative 4/3 power. Well, the first thing I'm going to do is deal with this negative. This whole thing will be negative 1/24 125 to the negative first, it'll actually become 125. So positive 4/3, dealing with negative exponent. Negative is reciprocal again. Now I'm going to deal with this exponent, so I'm going to use that rational exponent property. This becomes negative the cube root of 125 to the 4th power. I write it this way because I know 125 is 5 cubed, so this is really just negative 5 to the 4th. It's 4 negative, let's see, 5, 6, this is just negative 5 to the 4th power, which is just negative 625. Notice that since this negative is on the outside, the exponent is not being applied to it, which is why it is still there. Last question, square root of 250x cubed y to the 4th. There's a number of ways of simplifying this, but since it is a square root, I'm going to try to find perfect square factors. So I'm going to look at 250 and see if there's any perfect square factors in it. I know this is 2 times 125, which is 5 times 25. 25 is a perfect square factor, so I'll be able to remove the 5 from this radical, and I'll be left with a 2 times 5, or a 10 inside the radical. Next, we'll look at the x cubed. Well, x cubed is just x squared times x. This is a perfect square factor, so I'll be able to take out an x, and I'll be left with this other x to the side of the radical. Then my y to the negative 4th. Notice that this is, I should deal with the negative exponent, so this is actually 1 over y to the 4th inside the square root, which would be 1 over y squared. When I take that, so when I apply that square root, so I'll end up with a y squared in my denominator. This is my simplified tip. Rationalizing. You see rationalizing last year, the first time you saw it, you have a radical denominator. We don't like radicals in denominator, so we have to get it out of there. In order to do that, I'm going to multiply by another factor of the square root of 5. The top and bottom, what I end up with is 3 square root of 5 over the square root of 5 squared. The square root of 5 squared is just 5. So that's a quick and easy way to get rid of my radical. The only problem is when I try to apply that same process with the second example, if I only multiply by the square root of 3 over the square root of 3, when I distribute that square root of 3 into this denominator, it's not going to disappear. So we have that other process, when I have multiple terms in my denominator, is multiplying by the conjugate. The conjugate is basically the same terms with opposite signs, so that I apply that difference of squares property, and my middle terms will cancel out. When I distribute this, I end up with 25 minus 3 in the denominator, and 10 minus 2 rad 3 in the numerator. From here, our last steps is just to combine the denominators and simplify. Turns out, I end up with 10 minus 2 square root of 3. Since those are unlike terms, I can't combine them. Divided by 22. Then I'll just check to see if there's any common factors. There seems to be a common factor of 2. When I reduce everything by that common factor of 2, I end up with 5 minus the square root of 3 over 11. Final answer. In general, we can generalize this process, and in fact, I have on your formula sheet, if you go to your formula sheet, you'll notice that anytime we have a rationalization problem, if I was to multiply this by its conjugate, this is minus the square root of b, if I multiply by square root of a plus the square root of b over the square root of a plus the square root of b, I get a general formula that this will always reduce to square root of a plus square root of b over a minus b. You can either memorize that formula or memorize the process, but you will have to know how to reduce something of this type. Okay, last topic is factoring, and there's some basic process that you should check for every time you're factoring. First, we'll look for greatest common factor, then see if it's of quadratic type, and we have two ways of factoring types of quadratics. Basic quadratics, like you've seen before, and then quadratics like we have here. And whenever you see one where the leading coefficient is not 1, you're going to need to make a sum product box and then know what your sum and product will be. The sum is very simple. It's always this middle term. So it'll be negative 11 in this case. The product is this term times this term, which will be negative 12. It's sometimes called the AC method because I'm multiplying my A term times my C term. Once I have those two values, it's my job to determine what two numbers add to negative 11 and multiply negative 12. Looks like negative 12 and positive 1 will do that for me. And from here, we have two options. I'm going to go through the AC method, which is when we split this middle term into these two coefficients. So this will be minus 12x plus 1x. And I bring my other terms down. So this will be 3x squared minus 4. From here, I factor by grouping. My first term has a common factor of 3x. When I factor that, I'm left with x minus 4. And my second term has no common factor, so it'll be just plus this stuff. Notice now that there's a common factor of x minus 4, and when I factor that out, I'm left with 3x plus, there's really a coefficient of 1 here, and this is my factored form. You must use this process anytime you have a leading coefficient which is not 1. If it is 1, then you can factor by that normal double bubble method you've seen for the last 2 years. If you remember some of your special products like difference of two squares, sum of squares, perfect square factors, and another one which you must be familiar with is the sum and difference of cubes, which is again back on this formula sheet. Your sum and difference of cubes we'll write out right here. The sum of cubes factors to the following. I have my A and B term, my first term squared, the product of my two terms, and my last term squared. Now here's a way for remembering the signs. It always goes same sign, opposite sign, always positive, which spells out the word soap. So my sign here is positive, so it's the same, opposite, always positive. You repeat the same process for a difference of cubes. I have my A and my B term, my A squared, my double combined, my B squared, and again, soap, same sign, since it's negative here, it'll be negative here. Opposite sign, always positive. That is the formulas for factoring sums and differences of cubes. Let's apply those now to an example. Sorry, this seems to have disappeared. Okay. Let's apply that to an example, and this example will also include an example of factoring by grouping. So notice that it's a higher power. So the first thing I'm going to check for is see if I can factor out common factors from each group. It looks like the greatest common factor of my first group is an x squared. When I factor that out, I'm left with 27x cubed minus 8y cubed. For my second term, it looks like there's a greatest common factor of negative 1. I'm left with 27x cubed minus 8y cubed. I can now factor that out from each group. So I'm left with 27x cubed minus 8y cubed times x squared minus 1. My first term is a difference of two cubes, so I'm going to use that difference of two cubes formula. The cube root of my first term is 3x. The cube root of my second term is 2y. My first term squared is 9x squared. My two terms multiplied together would be 6xy. And my last term squared is 4y squared. Then my signs, same, opposite, always positive. My second term can also factor. It's a difference of two squares, so we'll factor to x plus 1, x minus 1.